Section 29 for the Bohr hydrogen atom. After Bohr came up with his idea for how the atom could be understood in terms of a set of postulates, he started working with those postulates to try and figure out whether or not he could come up with an analytic or a mathematical way of describing the specific states and transition energies for the hydrogen atom. And first of all, let's just start by reminding ourselves that an object moving circularly in orbit is kept in orbit by a centripetal force, which in this particular case is the Coulomb force between the electron and the nucleus. That Coulomb force provides the center-directed force that keeps the electron in its orbit. Excuse me. So we know what the Coulomb force is, and so we know how to describe that centripetal component. The Coulomb force is listed right here. It's E squared over 4 pi epsilon naught r squared, where E is the charge of the electron and the nucleus each, and r is the distance between them. And as we know, the centripetal force is directed toward the center of the orbit. And so the acceleration of that particle, the centripetal acceleration of the electron, is going to be the electric force divided by its mass, which we would equate with the centripetal force v squared over r, or the centripetal acceleration, excuse me. So on the left here, in this green circle, we have the Coulomb force divided by m, and on the right, we recognize that that's equal to v squared over r by virtue of the fact that the electron is traveling in a circular orbit, and therefore we can come up with an estimate of the electron's velocity based on the force that is exerted on it by the nucleus. And so v squared is E squared over 4 pi epsilon naught mr. And this is basically a constraint that's placed on the motion of the electron by virtue of the fact that, one, it's bound by the Coulomb force, and two, it therefore has a velocity and a radius that are in accordance with that particular force. The centripetal force is what causes the circular motion, and therefore the acceleration can be identified in terms of the Coulomb force, so that we end up with this expression for the velocity of the electron. Okay, now one of the assumptions that was also made shortly after the discovery that matter had a wave-like nature, Bohr assumed that in that orbit the electron would represent a kind of a standing wave, in that there were an integral number of wavelengths around one complete circumference of its orbit. Whatever radius the orbit was, that radius would then give rise to a circumference which Bohr assumed was some integral number of wavelengths, much like a standing wave on a string. And so that means that the circumference 2 pi r would be equal to some integer number of wavelengths of that electron. And of course the wavelength of the electron is consistent with its energy. Okay, so using the de Broglie wavelength formula, where the wavelength of a particle is equal to h, Planck's constant, divided by the momentum p, then we see that we can associate then the wavelength of the particle to be related to its velocity by this formula. Lambda is equal to h over mv. With that in mind then, we have the ability to link the velocity and the circumference of the orbit. The circumference is 2 pi r, and this is therefore equal to an integer number n times the wavelength of the particle h over mv. Now this is true only if the velocity of the electron is as we've assumed it to be. The speed of the electron is therefore related to the fact that the integral number of wavelengths fits on one circumference. So now we have another expression for the velocity. This formula for the velocity is based on the fact that there's an integral number of wavelengths around the circumference, and the wavelength is related to the electron's momentum and therefore its velocity. So basically the upshot of this is that we now have two ways to characterize the velocity of the electron. One in terms of the Coulomb force and the centripetal acceleration that Coulomb force gives to that electron, and secondly the relationship between the velocity and the wavelength or the circumference of its orbit. So there's a term that we want to become accustomed to. If we divide h, Planck's constant, by 2 pi, we end up getting what we call h bar. It turns out that this turns up often enough in the physics of atomic nuclear atoms, or the physics of small things in quantum mechanics. It turns up often enough that we give it a new name, which is h bar. And if you divide h by 2 pi, you find that that's equal to 6.58 times 10 to the minus 16 eV seconds. So that's one of the ways in which we'll see h. And if we characterize h that way, then we can now write the velocity of the electron based on its angular momentum and based on the fact that it has an integral number of wavelengths around one complete circumference as n h bar over mr, or in other words, n times the wavelength of the electron, which is h bar over mr. The wavelength is not h bar over mr, but this is the condition that says that the electron has an integral number of wavelengths around one circumference, and this is the velocity that therefore results. And you'll notice that it's n, an integer, times h bar over mr. So h bar over mr has the units of velocity, and the velocity, therefore, for the electron in the hydrogen atom, as viewed from this point of view, has an integer multiple of this fundamental quantity h bar over mr. So the electron, notice that we're actually dealing with it both as a particle and a wave. We're calling it a particle when we talk about the orbit and the Coulomb force that therefore binds it to the nucleus, as if it's executing a circular orbit around that nucleus bound by that centrifugal force. But we're also talking about it as a wave, in that once we're given that orbital radius and the circumference, we make the assumption that the circumference corresponds to an integral number of wavelengths of that electron. So equating both of these, we end up with this formula right here. Let's just look at this briefly. V squared is equal to, first, E squared over 4 pi epsilon naught mr. That comes from the fact that the velocity is related to the force that's binding the electron to the nucleus. The centripetal force from the Coulomb interaction provides, therefore, the force that causes the electron to go in a circle. And since the centripetal acceleration is v squared over r, we end up with this expression for v squared from the Coulomb force. And then the second expression, n squared h bar squared over m squared r squared, is from the recognition of the fact that the velocity of the electron is related to its wavelength, and the wavelength is such that over the course of one complete circumference, there's an integral number of those wavelengths fit on that circumference, much like, again, as a reminder, a standing wave on a string. So now we have two ways of characterizing the velocity, one from the Coulomb force and one from the wavelength condition of its orbit. And so as such, we can now, since both these expressions have the radius r in them, we can solve for r, and we find out that Bohr's analysis of the atom thus far seems to suggest that the radii are also able to be computed from these fundamental quantities. And you'll notice that the radius comes in values that are characterized by the subscript n, which is an integer. And so the radius goes up as n squared. For the ground state orbit, n would be 1, and therefore the radius for the ground state would be 4 pi epsilon naught h bar squared over me squared. And then the radii for the excited states go up as n squared times that quantity. So this first quantity for n equals 1 is called the Bohr radius. It should correspond to the radius of the electron's orbit in its ground state. And interestingly enough, with this very sort of simple theory that makes its assumptions based on some postulates, we end up with a value that actually is the Bohr radius of the hydrogen atom in its ground state. So this was one of the early victories of the Bohr model, the fact that it could predict the ground state radius so beautifully. The stationary states of the hydrogen atom therefore have particular radii which are equal to n squared times the Bohr radius, where n is 1, 2, 3, and onward. N is an integer, and the radii that the electron in the hydrogen atom is allowed to adopt are n squared times this fundamental radius. Now notice that this equation is based on the fact that the velocity of the electron takes on certain values based on the equating of the Coulomb force and the wavelength condition, and therefore the hydrogen atom can only exist if the radius of the electron orbit is one of these particular values. That comes from the fact that the radius comes as an integral multiple of one number really comes from the wavelength condition that we impose, and that is that the circumference is an integral number of wavelengths. Intermediate values of this radius cannot exist, and therefore the orbits themselves are quantized. The energy levels can also be therefore predicted. We know by energy conservation that the electron has both kinetic and potential energy. The kinetic energy is the motion around the nucleus, the energy of motion, and the potential energy is from the Coulomb force, the Coulomb potential between the electron and the nucleus. And therefore, we can say that the energy, being the sum of the kinetic and the potential, is therefore equal to this expression right here, 1/2 mv squared minus e squared over 4 pi epsilon naught r. Now notice, we can find the energies of these states when we first look at the velocities that result from this. If we solve for the velocity in this equation, we find that the velocity is equal to n h bar over mrn, which is 1 over n times h bar over mab, or the Bohr radius, or the fundamental velocity in the ground state divided by n. Therefore, the velocity goes down as a function of n. It starts off with the velocity in the ground state, which is v1. And from there on, for this n equals 2 and n equals 3 states, the velocity gets lower by a factor of 1 over n. Now, the energy for the stationary states therefore simplifies to the kinetic plus the potential, which we can now, once we've identified this way of characterizing the velocity, we can now express as this right here, negative 1 over n squared times 1 over 4 pi epsilon naught e squared over 2ab. This, therefore, is the energy of the orbits based on the conditions that we've already imposed and energy conservation, where the total energy of the atom is equal to its kinetic plus its potential energy. Okay, so we therefore can express this energy as 1 over 4 pi epsilon naught e squared over 2ab for the ground state where n is 1, and this comes out to 13.6 electron volts, which remarkably is the energy of the ground state of the hydrogen atom. And therefore we have this expression right here for the energies of all of the states in the atom, at least for the hydrogen atom, and it's equal to negative E1 over n squared, where E1 is the energy of the ground state, 13.6 electron volts. And you'll notice as n goes up, the energy goes down as 1 over n squared. This was a huge success of the Bohr model because it basically allowed us, with these very simple assumptions of the atom, the postulates that he originally came up with, and then the condition which amounts to the third postulate, and that is that the orbital radius contains an integral number of wavelengths. And just to remind you, that's based on the relatively recent discovery before Bohr that matter had wave-like characteristics. And so as he struggled to come up with a model for the atom, he figured it was natural to therefore suggest that the electron, with its wave nature, fits into orbits that are well-defined in terms of angular momentum and in terms of wavelength. So here's just a quick listing of the actual energy levels for the first couple of states in hydrogen. The ground state's at negative 13.6 electron volts, all the way up to the n equals 4 state at negative 0.85. Now keep in mind, these are negative because the electron is bound to the atom, and therefore in order to liberate that electron, we would have to give positive energy to the atom. In its ground state, we would have to give what we call the ionization energy to remove that electron from the atom, and we would have to provide 13.6 electron volts in order to do that. So these are the first 4 states according to the Bohr theory, and it turns out that they are reflected by the actual energies of the states of the hydrogen atom in nature. Now we've mentioned that this wavelength condition for the orbit has to do with its angular momentum. What that translates into is that when we start from the expression for angular momentum, which is mvr, we now have expressions for the velocity and the radius for the atom based on Bohr's postulates. And therefore, given this de Broglie condition, in order to construct a situation where the circumference corresponds to an integral number of wavelengths, we can now express that right here in terms of its angular momentum. Since this is the expression for the wavelengths relative to the circumference, and here we have the connection with angular momentum L, we therefore find that Bohr's theory, or at least this condition of wavelengths on the circumference, therefore dictates that the angular momentum of the electron is also quantized, and it comes in units of h bar. And so L is equal to an integer n times h bar. So the ground state would have angular momentum h bar, and then for n equals 2 excited state, it would have 2h bar, and for the n equals 3 state, it would have 3h bar, and so forth. So this is what the spectrum begins to look like. The ground state is at negative 13.6 electron volts, and then here are the excited states above that. The ionization point of the atom, where the electron is removed, can be removed from the atom, corresponds to the n equals infinity state. There's an infinite number of states technically that asymptotically approach 0 electron volts, or in other words, asymptotically approach the point where the electron is then free of the atom. It's bound most tightly in the ground state at negative 13.6 electron volts, and then we can give it that amount, 13.6 electron volts, to ionize the atom, in which case it leaves the atom with 0 or more energy if we give it. If we give it more than 13.6 electron volts, then it not only leaves the atom, but it leaves it with a little bit of extra kinetic energy. As far as the photon that leaves the system as the atom goes through transitions, this goes back to that postulate of Bohr's that says that the atom can make transitions from one state to another, and as it does that, we can compute the energy of the photon that leaves the system by virtue of the fact that the energy of the photon is h times f. Or in other words, the frequency of the photon is equal to the difference in the energy states, En minus Em, divided by h. So this gives us now the ability to predict the wavelengths of the emission spectrum for that hydrogen. Now, remarkably enough, if we when we express that wavelength in terms of the states, two states n and m, n might be, for example, the ground state, and m might be, or m would be the ground state, sorry, and then n would be the excited states. And so the condition for m and n is listed over here. M can be any state whatsoever, the ground state, the second state, the third state, and then n is going to be some state above that, some excited state above that, so that this expression right here for the wavelength is basically a replication of the Balmer formula, which we saw earlier. The Balmer formula, modified by Rydberg and Ritz, was one in which the pattern of the lines in hydrogen was able to be identified mathematically, and therefore they were able to come up with an empirical formula that would predict the wavelengths of the transitions. Now Bohr, based on his atom with a few basic postulate assumptions, is able to predict these levels, which was a huge success for the Bohr theory. And so finally, here's the listing of various transitions that we see in the hydrogen spectrum. The first ones to be discovered were the Balmer series, because they exist in the visible spectrum, and Johannes Balmer was the one that discovered not only that they had a pattern, but he was able to come up with the mathematical nature of that pattern. Since at the time they did not have the ability to do ultraviolet spectroscopy, they weren't aware of the Lyman series, which was later discovered with the advent of the ability to look at those lines outside the visible spectrum. So the Lyman series of transitions are ones that connect any excited state to the ground state. Those exist in the ultraviolet spectrum and therefore are not visible to the human eye. The Balmer series represents all of these transitions from excited states down to the n equals 2 state. Those are the ones that have energy that fits in the visible spectrum, and therefore those are the ones we see when we see a discharge of a hydrogen gas tube, discharge spectrum. So anyway, the Bohr theory in summary was incredibly and powerfully predictive in helping us understand the nature of the atom and the transitions that it undergoes, the hydrogen atom, that is. And so even though the theory was based on a few postulates that were taken as givens, as quantum mechanics developed later, Bohr and others were able to predict these behaviors, these features of the hydrogen atom at a deeper level, so that the postulates themselves, which then became better understood by the advent of quantum mechanics, gave even a better understanding of the hydrogen atom. And we'll get into that later.